So in the previous set of questions, we were looking at percent compositions and ratios. The ultimate version of these ratios when applied in stoichiometry is empirical formula. So let's introduce with a few easy empirical formula questions, and we'll move into determining it. So ADN has this structural formula. What's the empirical formula? Well, the molecular formula of this is H4, that's the 4 hydrogens, 4 nitrogens, 2 there, 3, 4, and 4 hydrogens, 2 there and 2 there. So the ratio of these atoms, which is the empirical formula, is just 1 to 1 to 1, because we just simplify it all by dividing by 4. So the empirical formula, HNO. Sosolone, one of the compounds responsible for the smell of raspberries. What a lovely compound. Give the empirical formula of this compound. Well, there's the structural formula. Molecular formula is equal to C6H8O3. Do note we had to stick in this hydrogen there. The examiner tried to fool us, but you cannot have a 3 bonded carbon atom, so we had to have that hydrogen in there. So anyway, what we see here is that this is as simple as it gets. We can't divide by 3 because 8 doesn't divide by 3 to give an integer. We can't divide by 2 because 3 doesn't divide by 2 to give an integer. Thus, this is the case where the empirical formula is the same as the molecular formula. I said no factor there, should mean, of course, factor of 1. There's HMX, another explosive. Molecular formula, counted all up, we got 4 carbons, we have 2, 4, 6, 8 hydrogens, we got tons of nitrogens, 1, 2, 3, 4, 5, 6, 7, 8, and then 8 oxygens. Hopefully you can see here that we got a factor of 4 all the way through, so divide everything by 4, and we get CH2N2O2 as the empirical formula. Okay, a large question of which we're only interested in a small bit of it. First of all, talking about compound G, its empirical formula is C2H2O, so its molecular formula is going to have the same number of hydrogens as carbons and twice as many of those oxygens. So now we look at the rest of it. It contains a carboxylic acid group. Now, carboxylic acid group, of course, contains 2 oxygen atoms, but here we've just got 1 oxygen atom. So therefore, the molecular formula contains 2 oxygen atoms, must be twice the empirical formula, which is C4H4O2. Not much of a formula for a really toxic compound, is it? Potassium permanganate used to maintain carbon-carbon triple bond, produce carboxylic acids, give the empirical formula of the alkyne that reacts in this way to give benzene, carboxylic acid, and propanoic acid. So to answer this, you need to know your organic naming. If you don't know that yet, just skip this one and move on. So anyway, benzene carboxylic acid is a benzene with a carboxylic acid group, and propanoic acid is, of course, CH3, CH2, COOH. Putting the organic-y part of this together, which is just the R1 to the C and then the C to the R2, we get this triple bond. So in other words, I've just gone backwards there, but removed all the oxygens and the OHs. And the molecular formula of this, 6 carbons, 7, 8, 9, 10, and then hydrogens, 5 there, plus another 5 is 10. So the empirical formula, divide that by 10 to get CH. A little bit sneaky if you haven't done your organic-y naming yet, but hopefully if I gave you these names, you can follow the logic from then on. Now we move into the standard empirical formula calculation type. Oxide of nitrogen contains 25.9% by mass nitrogen. Calculate the empirical formula. The way I like to do it is tabular. So I say percentage, 25.9 in nitrogen. The whole thing must be 100. So that's the oxygen must be 100 minus this, which is 74.1%. I then say, well, the percent is dealing with 100. So in other words, in 100 grams, we'd have 25.9 grams of nitrogen, 74.1 grams of oxygen. The reason I turn it into grams is because then we can divide by the molar masses to get the number of moles. I'm just tabulating this here. I'm not giving huge details. Hopefully by now, you know that to go from 25.9 grams of nitrogen to 1.85 moles, you would divide by 14. For the oxygen, divide by 16. Now we divide through by the smallest number, which is 1.85, and we get 1 and 2.5. That's the ratio of nitrogen to oxygen. However, we don't like our ratios with fractions in, so we clear that out by multiplying by 2. So N2O5. So another similar question pulled out from a larger question dealing with arachidonic acid. Interesting word. But we've got 25.44 carbon, some oxygen, some bromine, and the remainder being hydrogen. So therefore, there's our percentages. Add all those up, and you get the non-hydrogen part. Subtract from 100, and you get 3.42%. Convert that to grams in 100 grams, just the same numbers, just going from percent by mass to grams in 100 grams. Once you've got grams, divide by the molar mass of each atom to get the moles. And this is our ratio, but it's a rather ugly ratio. So what we do to turn an ugly ratio to a nicer ratio is divide by the smallest number. So divide by 0.212, we get 10, 1, 4, 16.1. Call that 16 between friends. So the empirical formula, 10 carbons, 16 hydrogens, 1 oxygen, and 4 bromines. Boranes, compounds made up of boron and hydrogen only. Gaseous boron, 78.14. So same thing, that's our 78.14% boron, 21.86% hydrogen. In this case, they told us the hydrogen. We could quite easily have got it by just dividing 78.14 or subtracting 78.14 from 100. Turn that into grams, turn that into moles. Ugly ratio, divide through by the smaller number, 7.24, and we get 1 to 3.02. Call that 3 between friends, so the empirical formula. BH3, aren't these easy? Compound Z, carbon, hydrogen, chlorine, 10.04% carbon, 89.12% chlorine. Add those up and you get 99.16, subtract it from 100 and you get 0.084% hydrogen. Turn that to grams, turn those to moles, and divide by the smaller number, which in this case 0.04, and we get 1 to 3 to 1. Thus the empirical formula, CHCl3. What other information would you need to decide whether this empirical formula is also the molecular formula? Well, the empirical formula is just a ratio, so it could be CHCl3, it could be C2H2Cl6, it could be C3H3Cl9, and so on. The other bit of information that is pretty clear is you would want the molar mass. You can get the molar mass experimentally, or you can use mass spec and hope you get the molecular ion or some other nice indicators. So finally, in this section, a combustion analysis problem in which they kind of take you through things. So anyway, a sample of 1.2 grams of acid F was burned in excess oxygen, F of course being one of these two acids. 1.79 grams carbon dioxide was formed. I calculate the mass of carbon present in F, and the idea is that all the carbon that is in F gets turned into carbon dioxide. So therefore the percent carbon in carbon dioxide is of course 12 over 44 times 100%, or 27.3%. So that means that the mass of carbon is 27.3% of the 1.79 grams of carbon dioxide, which is 0.488 grams. Several ways in which you could have gone to that particular one. You could have converted 1.79 grams of carbon dioxide to moles of carbon dioxide, and then from moles of carbon dioxide to moles of carbon, which is the same number, and then moles of carbon to this mass of carbon there. So several ways to do it. I just happen to like the percent one because it follows in with what we've been talking about with empirical formulas. So anyway, the mass of hydrogen in the sample is 0.061 grams. Assuming the rest of the sample is oxygen, calculate the mass of oxygen in the sample, and not exactly an A-level question. The mass of oxygen is the 1.2 grams with which we started, minus the 0.488 grams of carbon that we calculated in part 1, minus 0.061 grams of hydrogen, or in other words, 0.651 grams of oxygen. So we have the grams of carbon, we have the grams of hydrogen, we have the grams of oxygen. Thus in part 3 we can get the empirical formula of F. So that's where we are so far. There's the mass of carbon that we calculated, the mass of oxygen that we calculated in part 2, and then the mass of hydrogen that we were given at the start of part 2. As soon as you've got masses, convert them to moles, so dividing by 12, 16 and 1 respectively. Now divide by the smallest number and we get 1, 1, 1.5, which obviously I hope you would agree we just multiply by 2 to get the nice ratio. So 2 carbons, 1 times 2 is 2, 3 hydrogens, 1.5 times 2 is 3, and then 2 oxygens because 1 times 2 is 2.